Hi everyone. We had discussed how the periodic table is originally discovered. First, elements with similar properties are grouped together. Then it was discovered that if we order the elements based on their masses, there's a specific repeat or period for these grouped elements. That was just an observation. In this chapter, we will discuss a theory that explains why those repeats must exist and why elements in the same group tend to have similar properties. The theory was developed in the late 19th and early 20th century. It started with trying to understand the behavior of light. Light was understood to behave like waves in the ocean. To describe a light wave, we use the following properties. Wavelength is the distance that one wave travels. One wave is defined as the peak-to-peak distance in a wave. It has a unit of distance, or meter, and a symbol of the Greek letter lambda. Frequency is the number of waves that passes through in 1 second. Its unit is waves per second, or cycle per second, or usually just per second, or inverse second. Another unit is Hertz, or Hz, named after the person who studied frequency. The symbol for frequency is the Greek letter nu, which is given here. For example, if we take a stopwatch and measure how many waves go in 1 second, we see that for the first wave, only one full wave passes. This means that the frequency of this wave is 1 Hertz. If you look at the bottom wave, it has 3 full waves in 1 second. So its frequency is 3 Hertz. A third property is called the speed. The speed is how fast the waves travel per unit time, usually in 1 second. You can get the speed of a wave by multiplying its wavelength times its frequency, or lambda times nu. There's a number of physical phenomena that we can model as waves. Sound and light are two of these. Light is a special type of wave that we call an electromagnetic wave. And there is many different types of light based on the wave's frequency and length. The picture here shows the electromagnetic spectrum, which is the whole range of light that we know of. The light on the left has very short wavelengths and high frequency, while the light on the right has very long wavelengths with short frequency. One thing to note about electromagnetic waves is that they all have the same speed, which is called the speed of light and has a symbol c. The value of the speed of light in the vacuum is 3 times 10 to the 8 meter per second. Given the speed equation we had here, we can say that c is equal to lambda times nu. Of all the different lights that are given in this spectrum, the human eyes can only see a very small range, which we call the visible region. That's the color of the rainbow. When you go out of this range, we can't see the light. So for example, we can't see ultraviolet or infrared lights with our eyes. The discovery that changed how people look at light was done by two people, Max Planck and Albert Einstein. They discovered in succession that in addition to behaving like waves, light can also behave like a stream of particles, just like atoms are. This is what it's called the wave-particle duality of light. Light can be both a wave and a particle. The particle of light is called a photon. Each photon has an energy associated with it, which can be calculated using this equation. H times nu, or since nu, or frequency, is equal to c over lambda, we can also write h times c over lambda. H is the Planck's constant, which has the following value. Once scientists realized that light, which we always thought of as just a wave, can also behave like a particle, scientists started to wonder if other things that we always thought of as particles can also behave like waves. It turns out they can. Studies with electrons, which physicists had considered to be a pure particle, show that it can be diffracted, which previously were thought only to be the property of pure waves. Further work shows that the smaller the particle, the easier it is to observe this wave-like behavior. So atoms and electrons, which are very small particles, can easily be made to behave like waves in certain conditions. In fact, it makes sense to view both waves and particle as two sides of the same coin. Everything around us displays both properties, except that one behavior is a lot easier to observe than the other for specific phenomena. Okay, so let's now work on one of the examples on how to use the formula that I've showed you in the previous discussion. So the example I'm going to go through is this one right here that says, what's the frequency of a wave from orange light that has a wavelength of 602 nanometers? So we're given a wavelength, or lambda, 602 nanometers, and we're asked for frequency, or nu. And the way you want to approach this is you want to go back to one of the equations, which is this equation right here for light, where c is equal to lambda times nu. C, remember, is the speed of light. So if we start with that equation, and then we divide both sides by lambda to isolate the nu, we should get the equation at the bottom, which is nu is equal to c over lambda. Can cancel out one of the lambdas on one side. And once you have it in that format, then you can go ahead and plug in your numbers. 3 times 10 to the 8th meter per second for the speed of light. And the wavelength here is 602 nanometers, which you want to convert to meters to cancel out with the speed unit. And the conversion should look like that. And if you plug this into your calculator, you should get 4.98 times 10 to the 14 per second. And remember that that is a unit of frequency, or more commonly, we would just write it as hertz. At the same time that discoveries about the wave-particle duality were made, a new model of the atom was also developed by a physicist named Niels Bohr. He proposed that the electrons in the atom surround the nucleus, but only in specific locations, which he called orbits. This is very similar to the way planets orbit the sun. If the electron is in a lower orbit, where it is closer to the nucleus, it is more stable energetically because it makes attractive electrostatic interactions. Remember that opposites attract, and the electron is negatively charged, while the nucleus contains the protons, which are positively charged. If the electron is in a higher orbit, then it is less stable because it is further away from the positively charged nucleus. Bohr further explains that if the electron falls from the less stable to a more stable position, that is, from a higher to a lower orbit, it will release energy. This is similar to what happens when you drop a basketball. The ball will release energy to the surrounding. In the case of the ball, the energy is released in the form of heat, as well as pushing of the air particles around the ball, which generates the sound that you hear. For the electron, the energy released when it moves from a higher to a lower orbit is in the form of a photon of light. Bohr's theory is not just in his imagination. We can actually observe the light that is emitted by electrons that are falling in an atom. This is a picture for the hydrogen atom. For the hydrogen atom, the electron falling will generate the colors purple, blue, and red, as shown here. In fact, the technology that created neon signs, like the one shown here, is based on Bohr's explanation of the transition of electrons in atoms.